this problem, there are two identical spheres, so here and here. They each have mass m. They're hung from silk threads. Silk threads implies that these strings are not very heavy. Those masses don't matter. So they're hung from those threads. Each sphere is charged, and those two charges are the same. So Q1 equals Q2 equals Q. The radius of each sphere is very small compared to the distance between them. So these spheres are small compared to this distance. So they can be treated as point charges. If this angle is pretty small, find the equilibrium separation between the spheres. So how far apart are they? Once we set this up, release it, and it comes to rest. So let's start by drawing a free body diagram of either one of these masses. I'll pick the one on the left. So here's the mass. The forces that act on it, it has mass, so there is a force due to gravity. That's the weight. It points straight down. It has a force from the thread holding it up. That's a tension force. And if we label our angle in here, this angle is theta. And then the other force, the one that's pushing it apart, is the electric force. That's a repulsive force due to this guy. So this charge is repelled by this charge. There's an electric force that pushes this way. And in the bigger picture, there's another mass right here, and the distance between those two guys is the distance r. I'm going to label that distance on this picture up here so that this one doesn't get too cluttered. So from here to here is the total separation of the charges. After we do our free body diagram, let's identify the components. So the tension has an x component, Tx. It has a y component, Ty. This angle is theta, then this angle is theta. Now that we have our free body diagram, let's do Newton's second law. Let's say that the sum of the forces in each direction is mass times acceleration. Let's do the y direction first. Sum of the forces in the y direction is mass times acceleration in the y. In the y direction, we have the y component of tension, that's t times cosine theta. And in the negative y direction, we have force due to gravity, that's m times g. That equals 0 because this thing is not moving vertically. So that tells us that t times cosine theta equals m times g. So there's the first thing we have to work with. For our next bit of information, let's do the sum of the forces in the x direction. Sum of the forces in the x is mass times acceleration in the x. What we have in the x direction is the x component of the tension. The x component is opposite the angle, so we use sine, t sine theta. In the negative x direction, we have the electric force. The electric force is K, Coulomb's constant, times charge 1, that's Q, times charge 2, also Q, so we get Q squared, divided by the distance between them squared, r squared. And r is the distance from here to here. The two spheres have come to equilibrium. They're not moving, so the acceleration in the x is equal to 0. So that tells us that t times sine theta equals k times q squared over r squared. There's another equation we have to work with. So we're trying to find this distance r. We don't know t, but then we don't really care about it. So let's get rid of it by dividing this equation by this equation. So t sine theta divided by t cosine theta, so we divide the equations, is equal to kq squared over r squared divided by m times g. So if we look at this guy, we have the t's cancel. Sine theta over cosine theta, that's a result we know, that's tan theta, is equal to k times q squared over r squared times m times g. So now let's deal with this tan theta stuff, because we don't really know what tan theta is. One thing we do know is that the angle is very small. So if the angles are small, it means that tan theta is approximately the same. I wrote down tan, I should have wrote down tan theta. So tan theta, which is sine theta over cosine theta, Cosine theta is pretty close to 1, so tan theta is close to sine theta if the angles are small. Now let's look at our picture up here. Can we look at this picture and ask what is sine theta? So I'm just going to redraw it real quick down here. There's the length of the string, there's the mass, there's the vertical, here's the distance, and on the other side we have this mass right here. So this total distance is r, means the distance from here to here is r over 2. This angle is theta, so sine theta is opposite over hypotenuse. So sine theta is opposite r over 2 divided by the hypotenuse L. So tan theta, if theta is pretty small, is about equal to r over 2L. Let's put that result in here, and then we'll solve for r. So let's substitute in that result. R over 2L is about equal to k times q squared over r squared times m times g. We need to bring this r squared up here, gives us r cubed, equals, let's bring this 2L up here, k times q squared times 2L divided by m times g. Now to finish, we just take the cubed root, r is equal to k times q squared times 2L divided by mg to the power of 1/3, or the cubed root. So there's the equilibrium separation as long as that angle theta is pretty small.